Okay, here's a new definition. A function f is one-to-one if whenever f of a equals f of b, then a equals b. In short, what this is trying to say is if the outputs are the same, look, f of a is an output, f of b is an output, so when output equals output, the inputs are the same. Or, to say this a different way, the outputs are the y values, right? So if the y values are the same, it's because the x values are the same, or is it because it was the same x value. So notationally, it looks like there's a and b, though they looked different, they're actually equal. They're a equals b. So the horizontal line test that we have been talking about, it's actually the geometric version of this one-to-one concept here, right? It's this idea that if the y values are the same, it's because we were talking about the same x value. So in other words, to really boil this down, f is one-to-one, that is this thingy here is satisfied, if and only if the graph of f passes the horizontal line test. So we're trying to look at these new types of functions, or rather we're looking at functions which are one-to-one because if a function is one-to-one, the picture passes the horizontal line test, and that way the diagonal flip will pass the vertical line test. So to dig through some of the examples that we've already just looked at, so f of x equals 3x plus 2 is one-to-one since the graph y equals 3x plus 2 passes the horizontal line test, and because the graph passes the horizontal line test, when you look at the diagonal flip, that passes the vertical line test, and that diagonal flip is a function. Our second example was f of x equals 2 to the x. This is, to use the new language, this is a one-to-one function, okay, or this is one-to-one, since y equals 2 to the x, since that graph passes the horizontal line test, and since the graph pre-flip passes the horizontal line test, the post-flip picture, the flipped picture, will pass the vertical line test and is a function. Our third example was f of x equals x squared. This is not one-to-one since the original picture, since the pre-flip picture, y equals x squared, fails the horizontal line test, and therefore the post-flip picture, or the flipped picture, fails the vertical line test, and that flipped picture, in other words, is not a function. Now this flip, we'll see, switches really the roles of x and y. We can actually see this here that there's in the pre-flip, okay, this is the original, the x-axis is right here, the y-axis is there, and then once you do this diagonal flip, it's kind of hard to see here, but that's an x, and then this is actually a y, which is sideways, okay? The flip, actually, this diagonal flip changes, switches the roles of x and y, and you know, x was traditionally input and y was output, so what happens is that between the original function and this new function we're about to take a look at, the inputs become the outputs and the outputs become the inputs if you switch what roles x and y have. So this creates a new function. It is called the inverse, or the inverse function, and it is labeled in what looks like f to the negative 1, but the way we say this thingy here is we say f inverse. Now because the flip switches the roles of x and y, the domain of f is the range of f inverse, and the domain of f inverse is the range of f. This seems real profound, but really just recall what domain is and recall what range is. Okay, domain is the set of all inputs, and the range is the set of all outputs. So if the inputs become the outputs between one function and this new function called the inverse, it makes sense that the domain of one function is the range of the other function. Interactive question. Let's say that you have f being a one-to-one function, and let's say that you know that the point 3, 8 is a point on the graph of f. Then what point would you know on the graph of the inverse function? So think about something here, up here, which will serve to help you figure out what's going on with that.